If you haven't done so yet, please pause the video and try to answer the question first on your own before listening on. We've gone ahead and drawn a picture of the initial situation where the airplane initially is flying directly above the radar station 3 miles above. And the question notes that the plane is going to be moving 3 minutes in the forward direction at 200 miles per hour. So what we have to do is actually figure out how far horizontally it's traveled in those 3 minutes. And to do that, we can use a basic equation from physics or another course that you may have taken in the sciences. And that equation tells us that distance is simply equal to the rate multiplied by the time. The rate is essentially the speed. So we have 200 miles per hour, and then we're going to be multiplying that by the time of 3 minutes. The only problem, of course, is that time is given in minutes and the rate is in terms of hours. So we have to make a little conversion here. And what we can say is that 1 hour is equivalent to 60 minutes. And if we set up the conversion in this way, we can see that hours in the denominator will cancel with hours in the numerator, and then similarly minutes in the numerator here will cancel out with minutes in the denominator. That's going to leave us with miles. So we can pick up our calculators and type this in here. And when we do that, we end up with 10 miles. So in essence, the airplane has traveled horizontally a distance of 10 miles, although it's still located 3 miles above the ground. What we can next do is connect the radar station with the plane's current location with a straight line. And then what we need to do is also draw in the so-called angle of elevation. And the angle of elevation is formed by an imaginary horizontal line that projects from the radar station and the line that we just drew. So this angle right here, which we can mark theta, is going to be this angle of elevation. Now we're going to find it useful to project a line straight down here so that we can form a nice right triangle that includes that angle of elevation. And we can see from the diagram that if this length is 3 miles, then over here also would be 3 miles, so we can mark that in the diagram. And then also, if this length here is 10 miles, then this length right here also has to be 10 miles. Now, we need an equation that involves the angle theta so that we can actually figure out the rate of change in that angle. And to do that, we can examine this right triangle right here. And one equation that relates the distances and the angle would be the tangent equation. We know that the tangent of that angle is going to equal the opposite side, which we have marked as 3 miles, over the adjacent side, which we have marked as 10 miles. Now, because the question is asking for the rate of change in that angle, what we need to do is actually calculate the derivative of this equation with respect to time. Anytime a question is asking you to find the rate of change of a given quantity, it's asking you to compute the derivative with respect to time. In essence, in fact, this question is asking us to find the derivative of the angle of elevation with respect to time. So this becomes our big unknown in the question. We're going to go ahead and differentiate this equation with respect to time. And so on the left side, we're going to have to know the derivative of the tangent function, which turns out to be the secant squared of the angle. But then we have to multiply by the derivative of the angle with respect to time. That's basically an example of a chain rule, where you take the derivative and then you multiply by the derivative of the inside. And in this case, the derivative of theta will be d theta dt. On the other side, because we have a quotient, we're going to have to use the quotient rule. And that tells us to take the bottom, multiply it by the derivative of the top, which will be do dt, minus the top function, which is o, multiplied by the derivative of the bottom, which will be dA dt, and that will all be divided by the bottom squared. Now, to solve this equation for d theta dt, what we can do is divide both sides of the equation by the secant squared of theta. And when we do that on the right-hand side, that's going to put the secant squared of theta in the denominator here. It'll cancel out on the left-hand side. At this point, we can begin to fill in the values on the right-hand side of the equation so that we can actually solve for d theta dt. So we'll go one by one. Now, A stands for the adjacent side of our right triangle, and the side that's adjacent to that angle of elevation was equal to 10 miles. So we can plug in 10 miles in for A. And then dO dt, remember O stood for the opposite side. The opposite side of this right triangle is right here, and it's 3 miles. Now ask yourself, is that length or distance changing as the airplane flies along? And the answer is no, because as the airplane flies along, it's flying at a nice constant elevation of 3 miles. So this length is a constant throughout the problem, and of course the derivative of a constant is 0. So when it says d opposite dt, that derivative is going to be 0 because, once again, the opposite side is a constant length, and the derivative of a constant is 0. So now we have minus O, which is the opposite side of 3 miles, and then multiplied by dA dt. Now A was the adjacent side, so you have to ask yourself, what is the rate at which this side right here is changing? Now remember, that side is parallel to the side up here. And we can see from the picture that this side right here is actually increasing in length, because that's the airplane. And as it moves along in the rightward direction, this length right here is going to be increasing throughout the duration of the flight. So if this side is increasing, then of course this side also is increasing, because it's parallel. In essence, you can almost imagine that the airplane is down here flying along. And as it flies along, that's going to stretch out this length. And the rate at which it stretches out that length is simply the speed of the airplane. It's 200 miles per hour. So we're going to come in here and we're going to write 200 miles per hour. And that'll be the value of dA dt. And then we have to divide this by the secant squared of theta. Well, we know from some basic trig that secant of theta is the reciprocal of cosine. Now, cosine is adjacent over hypotenuse, so this would be hypotenuse over adjacent. We never found the hypotenuse, but we can using the Pythagorean theorem. A squared plus b squared equals c squared. And when you do that, you should end up with the square root of 109. If you have any questions about that, let me know in the comments. So that's the hypotenuse, square root of 109, divided by the adjacent, which is 10. But don't forget, we don't want secant of theta, we want secant squared of theta. So we would have to square this result, which is going to give us 109 over 100. So that's what we can fill in for the secant squared of theta. And as for the units, since we had a miles over miles, those units will actually cancel. Technically, these were miles squared over miles squared, but those units will cancel out. So we can just leave this as a unitless quantity. And then multiply by the adjacent side squared. So that's going to be 10 miles squared. Now, this term right here will drop out because we're multiplying by 0. We can pick up our calculators and multiply -3 by 200, and then divide by this entire quantity in the denominator. And when you do that, you should get -600 over 109. And then as for the units, if we look carefully, we can see in the numerator we had miles times miles, which is of course miles squared. In the denominator, we also have miles squared, so those are going to cancel out. But then we're still left with this unit of reciprocal hours. And so what we can say is that this will turn out to be radians per hour. Now, you might be wondering where the radians came from. One way of understanding that is to look back at what we're solving for. We're solving for d theta dt. So that means that the numerator must have the same unit as theta. And of course, theta is measured in radians. The denominator must have the same unit as time, which of course will be in hours. So this would be the answer in radians per hour. We can convert it to radians per minute if we wanted to by doing a little conversion that 1 hour is equivalent to 60 minutes. And if we set up the conversion in that way, the hours will cancel out, and then we'll have radians per minute. So you can pick up your calculator and multiply -600 over 109 by 1 over 60. And when you do that, you should get -10 over 109. And so that would be the correct answer in radians per minute.